Oh, hi everyone. Yeah, I'm Jiahao Kang from University of California, Santa Barbara. And today I'm going to share with you several works done on 2D device and circuits on graphene at Santa Barbara. First, I would like to appreciate and acknowledge my co-authors, Wei Chao, Devlina Saka, Yashin Katami, Wei Liu, and my advisor, Professor Cost of Banerjee. First, as we all know about the scaling issue of CMOS technology, we know that we need new devices with much smaller substrate swing and high current on-off ratio for the new technology. And as we know, TFET is one of the candidates. And we know that TFET has a very low off current due to the cut of the Boltzmann tail. And also it can have a very sharp turn on with substrate hot swing as much lower than 60 millivolts per decade. Also, it has a very high on-off current ratio. And although most of the TFETs are made from 3D materials, now I would like to motivate 2D materials for TFET. 2D materials are those kind of materials with layered structure, and between the layers, they are bonded with van der Waals force. And they have advantages in the ultra-thin body of them so that the carriers can confine in a very thin layers of about a few angstroms in the channel. While in 3D materials, the mobile charge central is always a little bit deep from the surface. So that in 2D, we can have better electrostatic control on the channel. And also, the source to channel and drain to channel capacitances in 2D materials can be much smaller due to ultra-thin thicknesses. Moreover, using 2D materials, several advanced topologies could be enabled. For example, we can make tunnel FETs with vertical structure with area tunneling by 2D materials. And on the other hand, 2D materials are, again, some variations. For example, in 2D materials, the thickness is always constant, and so that the band gaps is controllable based on the numbers of layers. While in 3D materials, we all know that it's like a potato chip, and the thickness roughness will induce some performance variations. And the other variation is the interface variation. In 2D materials, as all-in peel, the surface is ultra smooth without any outline doubling bonds, so that there is nearly no interface trap. While in 3D, because of the top atoms are not saturated, there are doubling bonds which may form traps at the interface. And now let's see what kind of 2D materials we have from this family tree. First, we have the graphene family, where we have graphene as a semi-metal. We have hexagon boron nitride as a dielectric. And also we have silicon and germanium. Well, there is another family which is named as a transition metal dichalconide family, where we have MOS2 and tungsten selenide, the two stars, as semiconductors. Also, we have superconductors, metals, and half metals in this family. Also, there are also different families with much complex structures, also layered materials, such as these ones. Now let's look into graphene, which is a 2D form of carbon, and it consists of an atomic thin layer of carbon atoms arranged in hexagonal lattice. And there are two bases in one unit cell. And this lattice is bonded by sp2 bonds in carbon. And there are also pz orbitals sticking out from the interface so that electrons can hop between these orbitals. And if we look into the electronic structure of graphene, we could see that the conduction band and valence band touch each other at 6 points, which are named as the Dirac point. And we can notice that the dispersion near Dirac point is linear, so that we have a close to zero effective mass for both electrons and holes. And due to the symmetry of the band structure, the electrons and holes are equal, which is different from silicon. For example, we need to make silicon devices as, for example, in PFET, we need to make the width as twice of NFET. But in graphene ribbons, we don't need to do that because the symmetry. And there is another advantage of graphene, which is the band gap tunability of it. we can cut graphene into nano ribbons so that we can open up a band gap. And this band gap is inverse proportional to the width of the graphene nano ribbon, as shown in this plot. And now let's look into what we can do with graphene ribbons in UCSB. We have done the research in passive devices based on graphene. For example, we research in graphene interconnects, graphene inductors, graphene transparent electrodes, and also we have done research in the active devices. For example, the graphene transistors, which may be in the form of the GNR TFET, GNR FET. And also we have proposed an idea where we use both graphene interconnects and the graphene transistor to make our graphene circuit. And based on the graphene transistor, we can make a TFET biosensor. Moreover, based on the graphene nanoribbons, we can make a negative differential resistance device, which is also a Isaki diode based on graphene nanoribbon. And using that device, we can make an ultra-compact SRAM cell. And another application is the floating gate memory based on graphene multilayer graphene as a floating gate. And in this talk, I will focus on these tunnel devices and circuits. And as we know, due to the band gap tunability and the field interface traps, graphene nanoribbon is really a great material for TFET applications. For example, we could achieve a very high on-off ratio and a very low substrate swing with graphene nanoribbons. And since we know the graphene nanoribbon and graphene interconnects have so many advantages, we could take advantage of them using this all graphene logic circuit idea, where we can make interconnects and transistor with the same material, graphene. Let's see how it made. First, we start with a single layer of graphene, and we etch it into ribbons, where the wide ribbons will act as interconnects, and the narrow ribbons will act as semiconductor used in transistors. And then we make the doping and oxide, and then the top metal layers. Then finally we make this logic circuits based on our graphene. And this is a two-stage inverter chain shown here. And as we can see, this technology really requires very few fabrication steps, and also the contact resistance can be very low due to the ultra-good interface between graphene and the graphene nanoribbons. And also, based on our evaluation, we find the performances of this circuit is really good, and it's much better than CMOS technology in terms of noise margin, gain, delay, and power consumption, compared with that of 22 nanometer CMOS. And we can apply graphene to another field. For example, as we know, Isaki diode for the past years, it suffers a lot from the interface trap, so that the peak to valley current ratio is really low for them. But now we could use graphene nanoribbons to reinvent this device. Here in the device, we use a heterojunction GNR with 2 extra gates. And by properly biasing those gates and the source and drain, we could make the device operating in different regions, and it can act as this as a Isaki diode. And the PVCR we can achieve with graphene nanoribbons is really high. It can be as high as 10,000, and also we could achieve high current density. And more exciting is that we could use 2 complementary devices, complementary GNR NDR devices to make this circuit. And as we can see, there are 2 stable points if we put the IV curves together, so that it can act as an SRAM cell. So it's very compact. It only has 2 transistors and with another access transistor. But for CMOS technology, we know that there are 6 transistors for SRAM cell. And also this SRAM cell can work at very low voltage operation. And the other idea is application of graphene as a floating gate in all to the floating gate transistor memory, and where the floating gate is made of multi-layer graphene, and the channel can be made from the single-layer TMD materials. Well, the advantages of this memory cell is that the graphene non-ribbon floating gates can immune to cell-to-cell interference, while the TMD channel can lead to a small VTH off and a small subthreshold swing. And also, we can find an additional barrier at the floating gate, which can suppress the leakage, so that we could enable further vertical scaling, which can extend the lifetime of the floating gate memory. And now let's move on our focus to a totally different domain, where the performances of TFET is not a big deal, which is the biosensor domain. As we know, that the TFET has very low off current. If we use it as a biosensor, we could achieve very low power in the off states and very abrupt turn on in the on state, so that this biosensor could be ultra sensitive. Compared with the conventional FET, the sensitivity can be improved by 10,000 times. Although there are so many opportunities for the graphene in tunnel device and circuits, there are also some challenges for it. For example, the synthesis of large area high-quality graphene is challenging, and we did something to avoid this challenge. For example, we can grow graphene with CVD with record high mobility, and we can control the number of layers, and also we can also control the stacking order of graphene, bilayer graphene, with the CVD method, where we can achieve high wafer scale, high quality graphene bilayer graphene with AB stacking. And the other challenge is the patterning of graphene. People develop different methods from both top-down and bottom-up method. And in UCSB, we can achieve sub-10 nanometer GNR pattern by e-beam lithography. And the thinnest GNR we achieve is 7 nanometer, as shown in this figure. And the next challenge is the doping of graphene. And people have developed many doping methods for graphene. For example, we have substitution doping, edge doping, intercalation doping, surface doping, and gate doping. But none of them are very stable and controllable in a small area of GNR. And the last challenge is the contact to the 2D materials. For example, for multilayer graphene, it's very necessary to contact to both the top and as well as the edge of the graphene ribbons. Because if we increase the number of layers, it's very difficult to contact the bottom layers. So we find that a few layers of 2D materials will be good for a device solution. And the other issues could be the interface properties, which can also affect the contact. For example, the property of orbital overlap, Schottky barrier, and tunnel barrier. And we have done research to all of these optimizations. And finally, we can achieve a FET with tungsten selenide with a record high on current and mobility, and with a Berkeley device. And okay, so that's it. Thank you.
Time of 1, 2 quick questions. Any questions? Yes.
So in many experiments, they see that the major problem with graphene nanoribbon is the edge roughness. But you showed some perfect result. I don't know, are these simulation or?
Okay, so thank you for your question. Actually, in our simulation for the graphene circuit, we have done the analysis of variations in the edge roughness. And in this first part of this paper, we didn't put these results in, but in the second part of the paper, which is still under review, we have that results. So it's somewhat against the variations, but it's not super robust actually. But also, I want to mention that the edge roughness is not a big deal for some reason because, for example, in some bottom-up method, the graphene non-ribbon scoring is very smooth without any edge roughness.